Okay, everyone. Today we're going to talk about a very important theorem in complex analysis. Uh, this theorem is Morora's theorem, and today we are also going to see whether we can use it to solve some problems, maybe in our homework or in your daily life. Okay, let's start. Morora's theorem. Well, it told us if U is a region in the complex plane, of course it's an open region, and if given a function f, which is continuous, and if this function satisfies the integral of it along every triangle gamma in this open region, and f must be holomorphic on U. Well, you may find you are very familiar with this theorem because it is very similar to the converse of Cauchy theorem. But indeed there are a little difference, and this difference is very important because in Cauchy theorem we assume that the region to be simply connected, and if f is a holomorphic function, then we can conclude that the integral along a simple closed curve of this function must be zero. But in Morora's theorem, we didn't require the region to be simply connected, and this characteristic is very important. We will study it much more deeper in the following exams. Okay, and now we try to prove this Morora theorem. Well, the key to prove this theorem, in fact, is as I mentioned, this U may not be a simple connected region. So we just what we need to do is to prove F is holomorphic on every open disk of this open region. Then since it's holomorphic on every open disk, then it must be holomorphic on the whole U. Okay, let's start. Now, since U is an open region, then for every A belongs to U, there exists a radius R which is greater than 0, such that the open disk centered at A with radius R belongs to this region. So now we try to construct a function capital FC, and this capital FC is defined by an integral along the integral of the FC along the this notation is the segment joining A to Z. You may doubt that why we define such a strange function, but in fact, this function is the antiderivative of FC on this open disk, and that's what we need to prove in the following proof. Okay. The key to complete the proof is that we try to construct a triangle in this open disk. So now we have 2 points, A and Z. If we choose another point, Z naught, in this disk, then there are 3 segments. Right? And the 3 segments must be a triangle. So since we have the assumption of Morora's theorem, the assumption told us that the integrand of the integral of Fc along every triangle in U is indeed 0. So if we integrate Fc along this triangle, the triangle we just construct, it must equal to 0. And we notice that this integral we can divide this integral into three integrals. Each integral is the integral of fc along each segment, a to z naught to z, and z to a. And you may find that the capital Fz is in fact the negative of the third integral. So if we move this integral into the right-hand side, and we can conclude that the capital Fz is in fact the first integral plus the second integral of Fz. And now we consider substitute z naught into the capital Fz. What we will find is that the second integral, if we substitute z naught into Fz, the second integral along this segment becomes just a point. So this integral just vanish. So Fz naught is just the first integral along the segment A, joining A to Z naught. So if we consider Fz minus Fz naught, the answer is just the integral of Fc along the segments joining Z naught to Z. And if we divided the two sides, divided the Z to Z minus Z naught of the on two sides, and the equation become like this. Then we use a very useful technique. Here we minus a Fz naught and plus a Fz naught. Note that this Fz naught is indeed a function, indeed a constant. And we know that a constant must be holomorphic. So if we consider the integration, the integral of this constant function along the segments joining Z naught to Z, the answer is just independent of the path we choose. So the answer is just the Fc naught times Z minus Z naught. So we put this Fz naught into the integral and left a positive Fz naught here. Well, if we observe this whole equation, and we may find if we take a limit, that is, if we let z converge to z naught, then this part is indeed the derivative of Fc. So if we consider this equation, if we consider this part minus the Fz naught here, and if we take the modulus, we want this the first part, the integral part, to be 0, so that we obtain that the antiderivative of Fz is in fact Fz naught. So we try to do this. Okay, we take the modulus of this part minus Fz naught, which is equal to the right-hand side of the equation, and also take a modulus. And we consider the integrand. So we integrated along the segments joining Z naught to Z, and A is not in this segment. So this is a compact set. And this function is actually holomorphic on this segment, on this compact set. So it must be bounded, okay? Because a holomorphic function, of course, it's continuous, and on a compact set, a continuous function must be bounded. So it has a supremum. And we take a modulus of 1 over Z minus Z naught, and we times the integral. So this integral is in fact the length of the segment joining z0 to z, and the answer is just the supremum of the integrand. Now, if we take a limit, that is, if we let z converge to z0, then this supremum is in fact converged to 0, because this segment become just a point. It's just 0. So we find the antiderivative of f z0, and at we find the derivative of capital Fz, and it's just Fz0. So we obtain that the f is the antiderivative of f on this open disk. And since this capital F must be infinitely differentiable, so it must be holomorphic. And so that F is also holomorphic on every open disk belongs to U. So F is, of course, holomorphic on U. So we complete the proof. And Morora's theorem is a very powerful tool that can be used to determine whether some function in a very complicated form is holomorphic. For example, a very classical example is the gamma function. But the proof of gamma function is holomorphic is very complicated, and it's include many details. So because of the time limitation, I don't want to go that deep. Instead, I want to introduce some basic application of Morora's theorem. For example, function defined by this form, the integral along a to b, the interval a to b of a function gtz, where t is a integer in this interval a to b. And let's see an example. Well, this example, it's given f is a function defined by an integral from 0 to 1, and the integrand defined by the square root of t over t minus c. And the domain is in fact the whole complex plane set minus a small interval 0 to 1. If you remember what Morora's theorem told us, that you may find that first of all, if we want to conclude that f is holomorphic on U, then first f must be continuous, and then the integral along every triangle in the region of this function must be 0. So this question, we have to first prove that f is continuous, and this is not easy, but we try to do this. Okay. Once we prove that it's continuous, and we consider the integral along every triangle in this region of this function, if we find it's equal to 0, then we can conclude that this f is indeed holomorphic. But first of all, we have to prove that it's continuous. Okay. Note that for every point A belongs to U, this U, in fact, is the region of the complex plane Z minus a small interval. It's open. So for every A in this region, there exists a radius r which is greater than 0, such that the open disk belongs to this region. So now we let delta is equal to r over 2. Then for every z belongs to the open disk, t minus z is in fact larger than. So this is just basic inequality. T minus the modulus of t minus a minus c, taken modulus. And we note that a minus c is in fact less than delta. So this part is larger than the modulus of t minus a minus delta. And delta is equal to r divided by 2. So we notice that since the disk center at A with radius r is in the region is in the region that the complex plane Z minus the interval 0 to 1. So this r must be less than or equal to t minus the modulus of t minus a, right? So this part is larger than the modulus of t minus a minus the modulus of t minus a, and we have to remember to divide it by 2. So we can conclude that t minus c taking modulus is greater than the modulus of t minus a divided by 2. So now we consider the modulus of fz minus fz minus fa. We use the definition of fz, and it's just the modulus of an integrand. Now we put the modulus into in the integrand, and this part must be less than or equal to the integral from 0 to 1 of this integrand. Now, since we have proved that the t minus c, the modulus of t minus c must larger than the modulus of t minus a divided by 2, then 1 over t minus z must be less than 2 over t minus a. And this integrand, we get rid of the influence of z, and this integrand is just a function of t, and we call it ht. It is a continuous function, and it's defined on a compact set, in the closed interval 0 to 1. Thus, it must be bounded. In fact, it can reach its maximum value. The maximum value exists as a real number m. Okay, so this inequality must less than 2 times the maximum of this of the integrand, and there is a z minus a left. Okay, and so we obtain that the modulus of fz minus fa is less than 2 times m times the modulus of z minus a, and we notice that it's the first order Lipschitz condition. So this fz must be a continuous function on the complex plane Z minus a closed interval. Now, what we are going to prove is that the integral of this function fz along every triangle of the uh, the region complex plane set minus this closed interval is 0. But we notice that this region is in fact not simply connected. So we use the same idea when we prove the Morara's theorem. Is that if we can conclude that the FC is holomorphic on every open disk of this region, then it must be holomorphic on this whole region. Okay, now we consider a open disk in this region, and we are going to show it's holomorphic in this open disk. So we consider the gamma as a triangle in this open disk. Since we know that by A, Fz is continuous function, then Fubini's theorem is hold. We apply this theorem, and we integrate this function from 0 to 1, and this function is in fact Fz, and we integrate Fz along the triangle gamma in this open disk, and we switch this to integral. We first integral the function square root of t over t minus z, and we know that this function is of course a holomorphic function in this open disk, so it's just a 0. If we integrate 0 from 0 to 1, then this integral must be 0. So we already know that the integral along any triangle in the open disk of Fz is 0. So by Morara's theorem, Fz must be holomorphic on this whole open disk. And since the open disk is chosen arbitrary in this in the complex plane set minus a closed interval 0 to 1, so it must be holomorphic on the whole region, on the whole complex plane set minus the closed interval 0 to 1. Okay, so this is power. So now we see that Morara's theorem is a very powerful theorem, and we prove some when we want to prove some function in a very complicated form, whether it's holomorphic. And in fact, we also found that another surprising result is a direct consequence of Morara's theorem, and we may regard it as a corollary of the Morara's theorem. And this corollary say that if U is a region in complex plane, and A belongs to U, given a continuous function which is holomorphic on U except one point we didn't know, it's the A point, it's the point A, then F is indeed holomorphic. So this corollary in fact tell us if we find a function is holomorphic in a region except one point, or we may say this function is almost holomorphic, then there is no choice. This function must be also holomorphic on that point we don't know. So let's try to prove this surprising result. Okay. The same way, since the region U is open, so there is this open ball center at A, which is belong to this open region, and if we consider a triangle in the open disk center at A, then of course there are three cases, and one of them exactly holds. The first case is that A is in the interior of this triangle, in the exterior of this triangle. Then and this situation is very simple because the interior of the triangle, in the interior of the triangle, F is holomorphic. So by Cauchy-Gauss's theorem, the integral along the triangle of FC must be 0. But the second case is much more difficult, because if A is in the interior of gamma of the triangle, then this time we may consider another small open ball in the interior of gamma, which is center at A, and its radius is epsilon. Epsilon is larger than 0. Then by Cauchy-Gauss's theorem, the integral along the triangle is equal to the integral along this small open disk. And we use a technique. We minus an FA and we plus FA back. So let's observe this integral, second integral. FA is in fact a constant, so it's holomorphic. So in this disk, in this open disk, it's a holomorphic function. So the integral along the disk is in fact this should be the boundary of the disk. Along the boundary of the disk, the integral should be along the boundary of the disk. Okay, so FA is a constant, so it's holomorphic. And a holomorphic function, if we integrate it along the boundary of an open disk, then the Cauchy-Gauss theorem told us that it must be 0. So we just omit this part. What about this part? This part, we should use the ML test to estimate the modulus of this integral. So first, we know that the FC is continuous, so FZ minus FA, of course, is also of course it's continuous. So there exists a very small delta for every Z belongs to the open disk center at A with radius delta. Fz minus Fa, the modulus must less than 1. That's the definition of continuous, right? So now we let the epsilon is less than delta, and by ML test, this integral is less than the integral of the modulus of Fz minus Fa along the boundary of the open disk. And obviously, since the modulus of Fz minus Fa is less than 1, the integral must less than 1 times the length of the boundary of the open disk. That's 2 pi times epsilon. And it converges to 0 as the epsilon converges to 0. Converges to 0 as epsilon converges to 0. So this integral, which is equal to these two parts, since the two parts are 0, then this integral must be 0. This integral along the triangle of FC must be 0. And now there is the third case left. Is that the third case left is that A is in the image of gamma. Now we try to modify the gamma. because A is in the gamma, and it's very annoying. So we modify gamma such that it goes around A along a semicircular arc of small radius epsilon instead, and A is in the exterior of this modified curve. Well, then it becomes easy because f is continuous as at A, so the line integral of f along the small circle arc and along the original small portion of the triangle both tend to 0, just like what we do in the second case. Using ML tests, therefore, we can also conclude that this integral along the triangle gamma of FC is in fact 0. So in 3 cases, the integral along the gamma of Fz are all become 0. So by Maurora's theorem, since Fz is continuous and the integral of it along every triangle in the open disk is equal to 0, then Fz must be holomorphic function on the open disk center at A. So Fz is holomorphic on the disk A. So Fz is holomorphic on A. It must holomorphic on the whole region U. Okay, that's all what we learned. Today we learned the important Maurora's theorem and learn how to use it to determine whether some complicated form function is holomorphic. And we also see a very important and surprising result, which can be derived directly from Maurora's theorem. Hope you learned something, and that's all my class. Thank you for your listening. Goodbye.